Okay, now we proceed our lecture with system response with additional poles. Okay, so far what we discussed is actually the second order system with only two complex poles but without no zeros. We can actually, with certain conditions, a system with more than two poles or with zeros can be approximated as a second order system with two complex dominant poles, meaning that if we have third order system, fourth order system, fifth order system, second order system with zeros, third order system with zeros, and so on and so forth, we can actually, with a certain condition, use the what we have learned so far, which the second order system analysis, to approximate the system with a higher order. So basically what we want to see is actually the system with a more higher order, which is a third order, fourth order, and so on and so forth. First thing first, what is the dominant closed loop poles? So the relative dominance of closed loop poles is determined by the ratio of the real parts of the closed loop poles, as well as the relative magnitudes of the residue evaluated at the closed loop poles. So the magnitude of the residue depends on both the closed loop poles and zeros. So we can say that if the ratio of the real parts of the closed loop poles exceed 5 and there are no zeros nearby, then the closed loop poles nearest the j omega axis will dominate in the transient response behavior. So let's say we have a system, actually I use this example, okay, comparing responses of these systems. So this is actually the first the control or the benchmark system. Okay, this is the second order system. And then we have T2 here is the third order system, which actually we have the same second order system here, but we add another extra poles here, S plus 10. So means this system is actually third order system. The T3 here, we have a third order system as well, but now we have the third pole located at S plus 3, which at negative 3. So the second order system here, the roots of the second order system is actually located at negative 2 plus minus 4.5323i. We have a system here. This is the second order system with the pole located at negative 2 plus minus 4.53i. And then we have another system. We have third order system is located at negative 10. So the second system is actually, it has this pole and also it has the third pole here at negative 10. And then we have a third system which has this, again, this two pole plus extra poles here at negative 3. And I have made a fourth system which located further to the left, which consists of these two poles here and another one at negative 30. So what we have actually, we have one second order system and we have three third order system. Okay, what I want to show you is that what are the effects of these third order poles at negative 3, negative 10 and negative 30. So from the previous lectures, I have shown to you, when we have a system, a pole that is located farther from the j omega axis, which For example, in this case, -3, -10, -30. So you can see here, -3, which the blue color here, decays slower as compared to the poles that is located farther to the left. For poles at -10 here, it decays much faster as compared to poles at -3, as well as the poles located at -3, which are represented by this orange plot here, decays much faster as compared to the poles that is located at -10. So we can conclude that when we have poles that is located farther to the left, the impulse or the response of the system is faster. It decays to zero faster. Okay, so means that when we have poles that is located near the j omega axis, it will affect the transient response of the second order system. Okay, let me show you. Okay, so this is how I plot this. So this is G1, and then this is how I plot G2, and this is how I plot this is alternative how to plot G2, GD2, and then this is GD3. So I use a different approach. I use a TFS approach. And then we have another one. We have GD4. Okay, this is a second order system. And then what we want to compare what happened when we add another pole at -10. So what happened is we have, you can see here, the red plot here, it is resembles the second order system. Why? Because we can say that the third pole at -10 located the ratio between the third pole to the dominant poles. Okay, this complex conjugate here is actually the dominant poles because it is located the j omega axis, and then there is no zeros nearby these two complex conjugate poles. Okay, and then for the system GD2 here, it is the third pole is located at -10, which you can see here, these two complex conjugate is actually -2 plus minus j omega. -2, so the ratio to this -10 is actually -10 to -2, which is about 5 times distance. So you can see here from our definition, we can say that if the poles of the third poles is located 5 times or more as compared to the second or the dominant poles, we can approximate the system to the second order. That is why you can see from the plot here, the red plot here resembles the blue plot. Okay, the blue plot is the second order system. The red plot is actually the third order system. Since the ratio of the third poles is 5 times, then we can say that this third order system, we can use the analysis that we have learned in the second order system. What does it mean? We can use the formula to find the TS, TR, TP, and so on, to find the values respectively. Okay, how about if we have another pole, we have another system that is the third pole is at -3, which is, if you can find the ratio, the third pole is at -3 and the dominant pole is at -2 here. So the ratio is less than 5. So you can see here the yellow plot here, the plot is different, much different as compared to the blue plot. So this third order system, the yellow one, we can say that we cannot use the second order approximation to find the parameters of this plot. Let's see another system which at negative 30. This is a third order system, and then the third pole is located at negative 30. You can see here the purple plot much closer in the shape to the blue plot, because the third poles of this system is located at negative 30. So you can see the ratio negative 30 divided by 2 is 15. So the ratio is 15 times. So the third poles located farther to the left 15 times than the dominant poles. So we can say that for this system, this third order system, we can use second order approximation to find the parameters of the time response. I repeat again, for the yellow plot here, okay, the yellow plot is actually third order system. What does it mean by third order system? It has 3 poles. 1, 2, 3. So the poles located at negative 2 plus minus 4.53i, and then the third pole is located at negative 3. So the dominant poles is this one, these two, because it is located much nearer to the j omega axis. Okay, so the third pole's distance to the dominant poles here is less than 5 time ratios. 3 divided by 2 is 1 point something. So when the ratio is less than 5, we can say that this third order system, we cannot use the second order approximation. What does it mean? We cannot use the formula that we have learned so far, TS, TP, TR, TD of the second order to find it on this third order system. Okay, for the purple plot here, the purple plot is a third order system as well. Okay, so what does it mean? It has 3 poles. So the first pole is here, negative 2 plus 4.53i. Second pole at negative 2 minus 4.53i. And then we have the third pole that is located far to the left, which at negative 30. So you can see the ratio of this third pole to the dominant poles here is negative 30 divided by 2. Okay, we only take this real axis pole, negative 2 here. So 30 divided by 2 is actually 15. So the distance, this third pole to this dominant poles is 15 times. We can say that from the definition, we can use this second order approximation if the ratio of the third poles is more than 5 times from the dominant poles. So in this case, if 15 times means that we can use all the formulas that we have learned so far for the second order system to find the parameters of this third order system, TS, TR, TD, TP, and so on and so forth. Okay, for this problem, what you can do is that you need to determine the validity of the second order approximation by the ratio of these third order poles to the dominant poles. Okay, so for this question we have 1 for 100. So we can actually find the roots, for this polynomial 1 for 100. So this dominant poles is located at negative 2 plus minus 9.798i. So what is the ratio of this third order poles to the dominant poles? It's actually 15 divided by 2. So the ratio is about 7.5. We can say that this system is we can use the second order approximation because the ratio is 7.5, which is more than 5. How about the question B? We have here 1 to 90. So we have roots of this polynomial 1 to 90 is -1 plus minus 9.43i. A third pole is located at -4, which we have 4 divided by 1 equals to 4, which less than 5. So we can say that for this second problem here, the B problem here, we cannot use second order approximation of this transfer function. We proceed with a system response with zeros. So from the first order system, we know that zeros only change the amplitude of the response. So how about for the second order system? Okay, so we can see from this plot, okay, let's say we have a system, second order system with no zero, this here. We have the zero is actually, the second order system actually, it has a dominant pulse at -1 plus minus j2.82, okay? Okay, how about when we introduce zeros at -3, -5, and -10? This is actually the same plot as you have seen in the lecture slides here. So how do I plot this? So this is how I plot these 4 transfer functions in the same plot. We can see here the blue line is actually a second order system, no zeros at all, and the pulse is located at -1 plus minus j omega d. We have a second order system with zeros. So the red plot is zeros at -3. Yellow plot is zeros at -5. Purple plot is a second order system with zeros at -10. You can see here, if the zeros is located near the dominant poles, okay, so here the red plot is the zero at -3. The pulse is at -1. So it affects the transient response of the system. How about -5? So -5 to -1, so it's about 5 times ratio. It's farther from the pulse at -1. So you can see the plot closer to the second order system with no zeros. But if we put the zeros much further to the left or farther to the poles, in this case the purple plot is at -10, so -10 divided by 1 is about 10 times ratio. You can see here the purple plot resembles the second order system plot here, the blue plot that has no zeros. So means that if the zeros is located further or distance from the dominant poles, the effect of the transient response of the zero will not be much of effect on the second order system. We can say that, we can say that if the ratios of the real parts of the closed loop poles exceed 5 and there are no zeros nearby, so in this case, if we consider only zeros in the second order system, okay, then the closed loop poles nearest the j omega axis will dominate in the transient response behavior because of these poles corresponds to transient response terms that decays slowly. So in this question, in this example just now, we have all of these plots is actually composed of second order system plus 1 zeros. The difference is only the location of zeros. Blue, no zeros. Purple, zeros at -10, which is a distance away from the dominant poles at -1. The yellow is at -5, which cukup makan lah, just enough. The distance is -5 as compared to -1, the poles at -1. And the red plot here, the zeros is introduced very near to the to the poles at -1. So we can say that for the red plot here, which is the second system here, is actually we cannot say that this is the dominant poles, because the zeros is actually affect the transient response, because it is located near the poles, -1 plus minus 2.82i. Okay, we have completed the time response analysis for this subchapter. So please read the summary here. Actually, what you have learned so far is you learn the first order system, which is very simple. What you need to know is the time constant. No, not so much information that we can extract from the first order system. However, for the second order system, the system become much more complex, and we can evaluate the system, and we can classify 4 types of response, which is overdamped, underdamped, undamped, critically damped of the system, based on the locations of the poles on the S-planes. Okay, and then we can we also have learned how to relate the damping ratio, the natural frequency, to the response of the system, as well as you have learned as well how to find the percentage overshoot, peak time, settling time, rise times from the MATLAB, as well as from the formula that we have derived and we have found in the topics. And we also learned just now about the effect of the third poles for approximation of the second order system. If we have higher order system, third order, fourth order, fifth order, and so on and so forth, if the poles located 5 times ratio, more than 5 times ratio to the dominant poles, then we can use the second order approximation to the higher order system. And lastly, we have learned about the effect of zeros to the second order system. So if we have a zero that is located near the near the poles, the dominant poles, it will affect the transient response. However, if the zeros is located much further away from the poles, the second order poles, the dominant poles, we can say that the effect of zero to the transient response is much less, and if further much further to the left, we can ignore the effect of zero to the overall system. All right, so I need to go back and do the revision because a lot of informations that you need to digest. However, if you understand the overall picture, there is not so much that you need to know about this subtopic.